Assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Well, you guys really seem to enjoy the trivia and cybersecurity tips that I started in last week's episode. So thank you again for the person that recommended the cybersecurity tips. And I guess to the Waveform podcast for giving me the idea for doing trivia in the beginning of an episode. And speaking of cybersecurity tips and trivia, let's get into this week's cybersecurity tip. So for this week's cybersecurity tip, my tip for you guys is whenever you're logging into a website, before you do anything, before you enter your username, password, or anything like that, first off, make sure it's using HTTPS, which basically ensures that your connection between you and the website is encrypted, so your password and username isn't being sent to the server in plain text, because that's bad. Because if you send your username and password in plain text, a potential man in the middle attack could happen, and someone could intercept your packets, find out what your username and password is, and then be able to log in with your credentials and hack you. So you definitely don't want that to happen. And the easiest way to tell if you have HTTPS is obviously if you look in the address bar and you see HTTPS, or if you see that little padlock thing, then you know that it's using HTTPS. And another thing you want to make sure, because some of these phishing scams are pretty crafty with this, and what they'll do is they'll tweak the URL, so you want to make sure you verify the URL is actually accurate and where you think you're going. So for instance, if you're trying to go to bankofamerica.com, make sure it's actually bankofamerica.com and not like bank 0F America with, instead of an I, it's a 1. So it looks like Bank of America if you're just kind of glancing at it quickly, but it's not. Or another thing I've seen some of these scammers do is they'll put like the actual URL. So it'd be like bankofamerica.com I don't know, some random string of text.com or something like that. So you see the Bank of America part and you're like, oh, it's Bank of America. And in case you weren't aware, there are tools out there used partly by the cybersecurity community to run like to do pen testing type stuff, or penetration testing. They'll like intentionally send out like phishing emails to companies in order to try to get them to fall for them. So there's tools out there that are made for these cybersecurity professionals, but obviously attackers use them as well, and these tools can literally generate websites that are completely identical to the real deal. So they could create a completely fake Facebook.com and then send you a phishing attack, and then you go click their link, and then you'll log in with your credentials, and then it'll just redirect you to Facebook, and boom, they got your credentials. So make sure whenever you're, signing into a website, make sure it has HTTPS, number one, and make sure the address in the URL is actually the website that you're intending to be on. So that's your cybersecurity tip for the week. Now, as far as the trivia goes, this one, I enjoy this question. So the question this week is, what is the maximum data transfer speed of a dial-up internet connection? So again, that is, what is the maximum data transfer speed of dial-up internet? Answer coming up at the end of the show. Now, before we get into the nerdy stuff, there's one thing that I want to touch on really quick, and ChatGPT is absolutely blowing up the internet right now. Like, everyone is going crazy for it, And I just think it is absolutely hilarious how a flutter like all the schools are, whether that's like grade schools, high schools, colleges, universities, all this stuff. They're all a flutter, and they're now trying to make tools to detect if you use, ChatGPT or some other kind of artificial intelligence to do your homework or write your essays or whatever, which I find is, kind of funny that they're putting all this effort into trying to create countermeasures to counteract ChatGPT. And New York City, their Department of Education has already announced that they're going to be banning the use of ChatGPT in schools, which, if you ask me, is completely laughable and totally hilarious, because if the New York City Department of Education actually thinks that banning ChatGPT at school is going to do a darn thing, they're out of their minds, because everyone and their grandma now has a smartphone. So, yeah, sure, you can put a firewall rule on your Wi-Fi that prevents, anyone from accessing ChatGPT. But one, then your teachers couldn't be able to access it. I guess you could maybe try to do like a user-based permissions thing to allow teachers to access it, maybe, if you're trying to get sophisticated. But students could easily just turn on a VPN, go off Wi-Fi and use data, and guess what? They have access to ChatGPT again. How about that? So, yeah, you blocking it is really not going to do anything. Not to mention the fact that students go home at the end of the day, and you can't exactly block ChatGPT on their home Wi-Fi. Now, sure, I guess one thing you might be able to do is you might be able to set some firewall rules on the Chromebooks that you give out to the students. You might be able to do some kind of like firewall rule on there to prevent like hardware-based firewall rule, operating system level, that they wouldn't be able to access ChatGPT. But again, they still have a smartphone, and I'm almost certain they have at least one other computer in their house that they could use. So right there, again, your plan is foiled, New York City Department of Education. So I really don't know. Like, you're basically trying to put a hurdle in front of the students, but it's like a twig on the ground. Like, I mean, I guess theoretically you could trip over it and fall, but like, it's really not hard to get around at all. Like, it's kind of a joke. So, yeah, like, what I want to know is, when did the point of school stop becoming about learning and turn into only mattering what grades you get and writing essays? Now, don't get me wrong. I know this has been happening for a long time, even back when I was, going through school, like grade school and all that. But at least back then, there was at least the facade that they still, at the core, cared about learning and were able to portray that. But now they're just like, oh, you're trying to use tools to get around our grades. We're going to try to crack down on you. It's like, wait a second. I thought the whole point of me going to school was to learn things. When did it only become about me having, grades and turning in assignments and that kind of thing? I thought it was about learning. Now, one thing I need to reiterate here, I've mentioned this, I don't know how many times on this podcast, but I'll say it again. I don't condone cheating, and I think you should do your own work. But at the end of the day, in the real world, you get to use the tools that are available to you. So if AI is available to you, theoretically, in the real world, you'd be able to use it. But, what do I know? And the second thing is, ChatGPT is not perfect. Now, personally, I have not played around with it, mainly because, well, I think now they, closed it off to new people because so many people got access to it and are playing around with it. And also, it wanted you to give them your phone number so they could do an SMS verification, and I wasn't about to give them my phone number because I don't want to give that kind of data out to, just some OpenAI just to play around with something. I ain't about to do that. And I know there's like tools out there that you can use to like auto-generate, to like send SMS to. I tried a few of those, none of them worked, and I just kind of gave up. But I did use a similar tool, which was developed, I think it was by U.com, called UChat or Ubot, something like that. And it's basically very similar to ChatGPT. And I will say, like, at times it's pretty good, and other times it's pretty blatantly obvious that it's not a real person. But anyway, that's neither here nor there. The point is that both that and ChatGPT are not correct 100% of the time. So even if hypothetically you told ChatGPT to write you an essay on X subject, you can't exactly just Control-C and Control-V that into your Word document and submit it. I mean, you theoretically could, you just would have the potential of having something blatantly wrong and your teacher being like, what the heck is this? So you would still have to read through everything that it wrote and make sure everything's correct, kind of put in your own time and effort, verifying things, tweaking things that you don't necessarily like the wording of or that are incorrect. So you still have to do some work. It's not like, I mean, I guess theoretically, like I said, you could just copy and paste it, but you would still want to do work to make sure it's, accurate and kind of, in your style and that kind of a thing. So it's not like, you just, do click and you're done on the essay. Like, I mean, you still have to do some work. But back to the point about schools being about learning. One thing that I do want to say before I go off on another rant here about schools is teachers definitely make the world a difference, because I know going through grade school, there were some teachers that I had that were just awesome, and they made learning so easy, and I hate to say it, but they made school, well, I won't say they made school fun, but they made learning fun. And the grades at that point just became an afterthought because you're so engaged in the learning and you're enjoying it, and because you're learning, the assignments they give you are essentially a joke because, they taught you so well and the assignments are just easy. So the grades become an afterthought. And if the grades are an afterthought, then there's no reason to cheat because they don't matter. And the other thing I think too is, a lot of these teachers that, are really good at their job and make it really easy to learn, I don't think they get enough credit or paid enough, but that's a whole nother subject that for some other podcast to get into. But the education system as a whole, if they honestly put as much effort into trying to prevent kids from cheating, like they're literally trying to create their own AI tools to detect if kids are using AI tools, which, by the way, that's just going to create an AI arms race. Just saying. But they already have tools to detect like plagiarism, like if you just copied and pasted somewhere from the internet. They're trying to create tools now to detect if you used AI. So if they put as much effort into trying to make sure kids aren't cheating and making sure their grades they're getting good grades and that stuff, and they actually just cared about fostering a good learning environment, they put the effort there, maybe cheating wouldn't become an issue anymore, because if they actually focused on the learning part, which is kind of the whole point, then the grades like I mentioned, the grades become an afterthought because you're learning and you know the material, so you don't have to really worry about, worrying if you're going to do good on this essay because you don't know the material that well, so you have to resort to cheating or, using other sources that maybe you're not supposed to, that kind of a thing. So yeah, I think this is really interesting with the whole, schools trying to crack down on ChatGPT, which I find absolutely hilarious. And then one other quick thing, which I guess now, I don't know if this technically counts as nerdy things. I'm not going to count it because it's a little different, I guess. But basically, the inspiration for this little rant here was I was watching a video about DNS, so the domain name system, and basically DNS, we've mentioned on the podcast before, but if you don't know, or as a refresher, DNS is basically the way that when you're in your web browser and you type in darkassassins.inc.com, for example, your computer has no idea what that means. It only deals in numbers. So the point of DNS is to take that darkassassins.inc.com and convert it to an IP address that your computer can understand and can, find its way to, which again goes off to routers and networking and all that good stuff. But the point of DNS is basically convert a name, something.com, .net, .gov, .io, whatever, and then convert it to an IP address. So that's the point of DNS. So the inspiration for this little rant here came from where they showed the IP addresses that were not legit. And when I say the IP addresses weren't legit, I don't mean that, like, if you type the IP address they had, on the screen and put it in your browser, it just wouldn't resolve to anything. No, I mean, like, they were literally impossible to exist. Like, one of the an IP address they showed was something like 192.168.275.569. Now, some of you might be thinking that sounds legit to me. I mean, it's, has the 4 numbers and the dots and everything, which, yes, it does have the 4 numbers and the dots, but it's also wrong because IP addresses are split into 4 octets. Now, as you might be able to guess from the name octet, that means an 8-bit number. So it consists of 4 8-bit numbers. Now, assuming that these are unsigned numbers, which in the case of IP addresses they are, the maximum value an 8-bit number can be is 255. So if you have an IP address with a number that is either less than 0 or greater than 255, it's not valid. It is literally impossible to exist. But we're kind of getting ahead of ourselves here. Like, what the heck is signed and unsigned numbers? What does that even mean? So the first thing that we kind of have to do and think about is computers only see numbers as ones and zeros. They see them as binary. So in binary terms, binary data, it's a 1 or a 0, and these binary values are known as 1 bit. So if you have either a 1 or a 0, that's 1 bit. So when we talk about an 8-bit number, there's 8 ones and zeros in this number. And binary is obviously base 2, so, 2 to the power whatever is the number that you can have and represent. So, and when it comes down to computer data, everything is converted to just ones and zeros at the end of the day. So everything from your family photos, videos, complex computer programs, numbers, everything is just stored as ones and zeros. So when it comes to how do you distinguish between positive and negative numbers, that's where, because obviously if it's just a 1 or a 0, I mean, sure, you can represent, a large number, like, yeah, you can represent, any number really in ones and zeros, but how do you distinguish if it's negative? And that's a signed number is a number that can be positive or negative, and an unsigned number is a number that can only be positive. So the way that you distinguish this is you take depending on what kind of notation you're doing, if you're doing big endian or little endian, all that is which way the numbers are sorted, or represented. So in one case, the largest number value is on the left, and in the other, the largest value is on the right. So basically what the signed and unsigned does, though, is wherever the largest number value is located, that bit becomes the signed bit. So if it's a 1, that means it's signed, which means it's negative. And if it's a 0, that means it's not signed and it's positive. So, but because you're taking the largest, bit in the number, you essentially cut what the maximum number you can represent in half because you're representing positive and negative numbers. So if we go back to the 8-bit example here, so if the first bit, the largest bit, represents positive or negative, then you're only left with 7 bits left to represent a number, which means you can represent a maximum of 2 to the power of 7 or 127. Now, those of you who are saying, but 2 to the power of 7 is 128, you're correct, but remember, computers and computer scientists, we start counting at 0, so 0 to 127 is 128 numbers. So going back to if you have an unsigned number where you don't have to worry about that first bit being indicating positive or negative, you can represent values 0 to 255 because that's 2 to the power of 8, which is 256, but remember we start counting at 0, so you subtract 1, so that's where you get the 255. And then if you're representing signed numbers, you can represent negative 127 to 128. And the reason you have that extra on the positive side is because, again, you only have 1 0, so that subtracts, and, that's where it comes from. So it just kind of moves your window range of where that 256 numbers you can represent is. It just kind of moves that range around. So yeah, I just thought that was interesting. I'm not sure if they just kind of didn't think when they put that number in there, or if they just didn't know how IP addresses work. I'm not sure. But anyway, I thought I would, clarify that. Thought it'd be a good learning experience for all of you, are kind of how signed and unsigned numbers work. So with all of that preface out of the way, let's get into what nerdy stuff have I been up to this week. So, if you recall, before Christmas, I tried to install macOS Ventura on basically all my Macs, and it did not go so well. Now, this week, I tried it again. Well, I didn't try it on all of them. I tried it additionally on my Mac Mini, which, if you remember, it worked initially, and then somehow it got corrupted and wouldn't boot, and I had to completely wipe the drive and all that stuff. So I tried to install Ventura again, and it worked, which I was like, okay, we've been here before. Let's see if it's stable and will continue to work. And so far, knock on wood, I have not had any issues with it, and it's been working fine on macOS Ventura, and everything's good. So we'll see how that plays out in the future, if it stays that way, or if it crashes and burns again. But other things I did, if you remember I made a whole script to check if my router was up, because I had that issue where, for whatever reason, the network card would just disconnect and my internet would stop working. Well, this week, I noticed my internet wasn't working, and it was right around the half-hour mark, so I knew that my script was about to kick off. So, of course, what I did was I checked my router, and of course it was down. And I was like, So then I watched my logs, and I see my script kick into action, see that the router's down, kick off the Ansible playbook. And mind you, I'm actually getting to watch this in real time. And then I see that the Ansible playbook completes, the router's back up, and wouldn't you know it, my internet works again. So the script works, and it was so cool that I got to see it in real time that I was really happy about that. Which, another thing that is kind of funny, later on this week, I actually was looking through the logs again, and I saw that it actually had to do this playbook again and restart the router again, which I didn't even notice it did that. I actually don't remember what time it was. It might have been in the middle of the night or something when I was asleep. But regardless, it's done it multiple times, and my internet has continued to work through it. So thumbs up to that script. Now, I also mentioned in last week's episode, because I lost connection to my home lab because my router went down, because power went out and my router wasn't set to go back to its previous state and turn back on in the event of a power outage. So I've implemented basically all those ideas that I wanted to into the backup script. So I did some parallelism. So my backup script will now, once the NAS archives the data, it will begin the checksum process in parallel to copying the data over to the Xserve to slash some of the runtime, which is going to be awesome. Haven't tested this on the large scale, but doing a small scale test of a small folder, everything worked perfectly. So we'll see next time I do any kind of traveling or I'm away from home. We're gonna fire that bad boy up, and we'll see if it works. But hopefully it'll work. And then some other things that I added some stuff to the Ansible config, so it'll tell me like how long each task took in the playbook. So I'll be able to see like, okay, the archive process took 3.5 hours or whatever the case may be. So I'll be able to see kind of where all the time's going. And because it's running in parallel, what's going to be great is if you actually sum up all the time from all the Ansible tasks, it's going to be more than what the total time's going to be, at least in theory. But in my small scale testing, that was the case. So I guess we'll see what happens there. So that was some of the nerdy stuff I did. But now comes the big thing that I want to talk about, which is I think I have found a use case for a cluster of computers. Unfortunately, it's not Kubernetes because I still haven't found a good use for Kubernetes, but I have developed possibly the world's first dynamic distributed or cluster compiler, which I am very, very proud about. Now, in doing some research about essentially this idea of having your source code be distributed across multiple different computers and compiled and joined together to create one application. Initially, I couldn't find anything, and then I found I think it was a Raspberry Pi forum of all places. Someone had a link to a program called distcc, which is a distributed C, C++, and Objective-C compiler, I believe. But that solution only works with those specific languages, like only like certain C languages, whereas my compiler is able to do any language that uses a makefile. So not only can you do C programs, C++, Objective-C, any of the C family that uses a makefile, but you can also do other languages like Java, Rust, Go, literally anything that you can write a makefile for. This compiler will be able to distribute it across a cluster of nodes and have all of them work together to compile parts of it and then join it into one application at the end. Now, some of you might be thinking, so I guess there's probably, I hear two people right now. The one person is saying, wow, that sounds really cool. And the other person is saying, that's a stupid idea and you're an idiot. And both of you are absolutely correct. So before we kind of get into the specifics of how it works, I kind of want to just talk about the premise of a distributed or a cluster compiler. So the premise of this is when you're compiling code on your local machine, or maybe you're compiling it on a remote server, you're limited to the number of cores that machine has. So the idea of a distributed compiler is you divide up the source code amongst all the different nodes in your cluster or whatever, however many you got, and you divide it up evenly, and then each one of those computers compiles their assigned source code files, and then at the very end you have like a master computer that takes all those compiled files and joins it into the application. So if you had a absolute chungus of a source code, you had an absolutely massive amount of source code files, and your application was massive, you could potentially see some decent speed up from this by, if each computer was able to, compile, I don't know, maybe like 30 of the source code files, rather than, one machine having to compile, say, all, I don't know, 500 files, right? And then join everything together. So that's where you could potentially see some speed improvements. But as you might be able to kind of tell, it's a lot more complex than it has to be. It's the idea of having to distribute source code amongst servers and having them all work together and making sure that all the source code is in the same place, and you have the header files and libraries that all the nodes need to compile the source code is all together, and you're not overwriting files. There's a lot of complexity here and a lot of overhead, which is why I don't believe this is necessarily a popular idea. Plus, going back to the overhead thing, if you have a really small application with only 5 or 6 source files, it really makes zero sense to distribute it across, a cluster of nodes, because unless you're just doing it for the cool factor, which, I mean, I don't know about you, but going up to someone and saying, yeah, I compiled my program on a cluster of servers, I mean, that's quite the flex. I'm not going to lie. That's a pretty big flex. But aside from just kind of doing it because you can, it's not exactly that practical, which if you think back to the episode that we did on multiprocessing and multithreading, it's kind of that, but on steroids, because the point of multiprocessing and multithreading is to take a task and be able to speed it up by either dividing it up to have more threads to maybe handle input-output, or you have a lot of processing that can be done in parallel, so you do multiprocessing. But the point is to take a task and speed it up. But in order to take that task and speed it up, you have initial overhead in having to split up and, do any kind of things ahead of time to make sure that you're not going to have any kind of deadlock situations, or essentially make sure that you can run everything in parallel, and the operating system has to do stuff on its end to, divide up the sub-processes or divide up the threads or whatever, and allocate CPU time and all this stuff. So it's not, instant performance. Like, there is some overhead and a little bit of initial hit to performance, which is why if you can't take advantage of multiprocessing and multithreading, you can actually see a performance hit by doing that. So it's obviously the same thing here with distributing your source code amongst a cluster of servers. If you can't take advantage of all that extra processing power and be able to take advantage and, be able to absorb that massive overhead, if you can't take advantage of that, you're just wasting your time. But if you can take advantage of that, then you could potentially see some really big speed improvements, because if, say, you only can compile, 8 source files at a time on your 8-core machine, if you had, a cluster of servers with a combined, I don't know, say 128 cores, I mean, that's a big improvement that could potentially, make your code compile a heck of a lot faster. So in Makefiles specifically, if you're creating a Makefile, if you didn't know this, when you run the make command, you can tack on a -J flag. If you tack on -J, you can specify how many jobs you want to run. And generally, you probably don't want to run more jobs than your computerized cores, because then you could run into issues where you basically have errors because you don't compile all the files. So basically, you take the -J to run multiple jobs, but then you also do another layer on top of that and distribute it out to a bunch of other servers. So it's definitely a lot of complexity there. And one thing I haven't mentioned, at least in my solution, I can't speak for the dist-cc, but in my solution, if you have, first off, you have to be running the same operating system. Or somehow, if you put it in your makefile, you could specify a specific compiler. If you're on a different operating system, maybe that could work. But if you're on different operating systems or using different compilers or don't have certain installed system libraries or whatever, you're probably going to be in for a bad time, because if you've ever tried to compile some of your source code on, say, a Windows machine, some other source code on a Linux machine, and then you try to combine it all on a Mac, it's not going to go very well. So you want to make sure all of your servers in your cluster are running the same operating system, which is kind of a limitation, because then you'd have to have a different cluster for each operating system, which is potentially a drawback, depending on what you're building for. And the other thing you have to keep in mind is, how are you getting the source code to each one of these machines? Because if you're copying the source code to each machine individually and then having them send back the object files, that's going to be an absolute nightmare, because if you've ever tried to transfer small files, whether that's over the network or on a USB drive, you know that it is significantly slower than if you're transferring one large file. So even adding more to the overhead. So my solution was, rather than transferring all the files across the network like that, my idea was you would essentially have your source code on some kind of centralized location, like a NAS, for example, that all the nodes in your cluster would then be able to access that directory on the NAS and be able to compile on the NAS itself. That way you don't have to worry about copying a bunch of files back and forth. You're just working off the NAS. So, I mean, you still have a little bit of latency with the networking speed, but it's going to be a heck of a lot faster than manually copying over the source files for every single node, and then once they compile their program, copying it back to you. Because like I mentioned before, the other thing that you have to keep in mind when you're distributing this code out is header file, like in the case of like C programs, header files, or if you're dealing with Java programs, other Java files. Because if you have a file and it's looking for a file that doesn't exist, it's not going to compile. So you have to make sure that somewhere centralized to all the nodes is all of the header files or all the requisite files that are needed by other files. Because if you distribute, say you distribute the main.c file to node X, but main.c is trying to include random.h, which is on node Y, if there's going to be an issue there, because node X is going to be, when it's compiling main.c, it's going to be looking for that random.h file, but it's not going to be able to find it, and it's going to error out and not work. So you have to make sure that there's a lot of things you have to keep in mind when, planning something like this out. So another thing, I guess, that you have to, that at least in my solution they had to keep in mind, is the makefile for just your standard makefile is different than this distributed makefile, because, like I said, because you're distributing the source code out to all the different nodes, you don't want them to compile all the source code for the project, because then that just defeats the purpose. But you also have to make sure that you list out all the output or object files or whatever the case may be that are required to build the executable, because if you don't do that, then your executable is not going to work. So in normal makefiles, how you do this is you just have, like, if you're doing makefiles with variables, you make one variable that is your object variable that contains all the object files, or class files if you're like using Java or something. But you have one variable that contains all the files that go into the executable. But if you're doing the distributed makefile, while yes, you want that, you also want to know what the source files are that you need to compile in your current directory, and only those files, because those are the only ones that you want to compile, because otherwise you're doing work that someone else is doing. And if every node in the cluster is just compiling the entire project, that completely defeats the purpose of distributing the source code across a bunch of different nodes in a cluster to compile the program and join it back as one program, right? So if node X, Y, and Z all compiled the same program and did the whole thing, what was the point? You could have just done that on your local machine, right? So that's another thing you have to keep in mind in this solution, is you have to essentially it's a custom make file in a sense, but in all reality, there isn't a ton of tweaking that you really have to do. In the one example that I currently have that I've been using for testing, there's really, I think, only 3 changes, and those changes are: I changed where the root directory is, because it's going to be nested somewhat, so you have to kind of go out an extra directory before you can go back into where the header files are. And then in addition to that, then like I mentioned, there's that extra variable for only getting the object files in your current directory. And then I think I added 2 specific rules, one for building the application itself, and then one for building just the object files that are in your current directory. So then when this makefile, or when all the source code gets distributed to all the nodes in the cluster, they all can use the same custom makefile. You don't have to have a makefile for each individual node. You can just have one makefile that gets distributed to all of them, and it'll work the same, and it'll run the rule in the makefile that tells the node to compile all of the source code in its folder. And then it'll compile that and then move its compiled object files or class files or whatever the case is to the central location, where when you actually try to build the application itself, that's where it looks. So when you're trying to build the application, if all of the object files are in one central location, you don't have to rebuild anything, and you can just link them all together and make your executable. So that's kind of another thing that you have to keep in mind, which theoretically you are doing anyway with make. Putting all of your object files into one location, it definitely makes it easier to, when you go to clean your source directory. If you just have all of your object files in one folder, then you can just delete that folder and you're good to go. So if you have a designated folder, say you're doing this on a NAS, right? Your source code's on the NAS, and when you're building your source code, you have your make files output their object files that they create when they compile the source code into this object files directory, also on the NAS. And then when your makefile goes to build the executable, once it becomes that time, it looks in that objects directory and makes sure that every object file that should be there is there, and then it can build the executable. So if all of your nodes are building into the same object directory like you normally would if you're building it, just on a single machine, then when you go to build the executable, you don't have to rebuild anything. So that's kind of, I guess, the genius, I guess you could say, of the distributed compiler is you take all these nodes with source code from who knows where in the project, assigns it where it's supposed to go in the object directory, and then you have the master node at the very end that just links everything together and creates the executable. So now, after explaining all of this, you can probably see the issue of why this generally isn't done, and why it's not a very popular solution, because of how complex it is and how much overhead it is and the infrastructure you need to have and a bunch of stuff that goes into all this just to be able to make this even work. Which I guess on the one hand, though, you could mitigate this if you were just compiling a Java program, because Java can run everywhere. You build it once and run it everywhere, or as some people like to say, you build it once and then exploit it everywhere. But that's another conversation. But obviously, if you haven't guessed, with this orchestrating of a bunch of servers in a cluster, if you haven't guessed, I'm using Ansible for this because Ansible is awesome. But as far as the compiler itself, I just wrote that as a Python script, which I know the hardcore people are going to be like, you can't write a compiler in Python, you have to write it in C or Rust or C++ or some other low-level language, which, don't get me wrong, I hear what you're saying, and I actually thought about rewriting it in like C or C++ or something. But then I got to thinking, the runtime of the actual Python script itself is so much shorter than the Ansible playbook running that it really doesn't matter if I shave like a couple tenths of a second off. It's still going to take a while to run because of the Ansible playbook. So at the end of the day, I decided, I'm not going to rewrite a few hundred lines of code just to put it in like C or C++, because that's how, quote, compilers are supposed to be written or whatever, which, as I guess as you might be able to tell here, while I'm calling this a compiler because it can compile projects, it's not actually doing any of the compiling itself, which actually, going back to distcc, from what I looked into on that, that's essentially doing the same thing that I'm doing, which is essentially just being a front that then uses other compilers to actually do the compiling for. So me and them were kind of thinking on the same wavelength. But then again, having tested this and all that stuff, and you hearing me mention how it works, is this practical at all? No. Absolutely not. And in all honesty, it's probably going to be a heck of a lot faster compiling it on your local machine than trying to distribute it across a cluster of servers, unless, like I said, you fall into that niche category where your code base is just so darn massive and you have so many source files, and those source files are so huge that you can actually take advantage of a distributed compiler and you can make up all of the time lost in the initial overhead. In that case, yeah, sure. But in most people that are writing programs, is it going to be faster than compiling it on one machine? Heck no, it's not. But you can bet your butt that it is cool as heck. And as we mentioned in a previous episode, the cool factor by itself gives it performance. So yeah, it might be 50% slower in a certain use case, but because it's so darn cool that you compiled a project across a cluster of servers, I mean, that's at least the same speed, if not faster, doing it on the cluster because of how darn cool it is. So yeah, but yeah, the concept that I was working on, which is just like I think it had like 3 source files and like 2 header files or something like that. I mean, it was like milliseconds compile time, like locally, and then seconds compile time across a cluster. So yeah, obviously not faster. But again, that's if you're only having like 5, total files, that's not the use case for something like this, right? The use case for this is, like I mentioned, a massive code base that can take advantage of multiple servers and more processing power and more compute power than a single machine can provide. So this was a little bit of a longer episode, but I hope you enjoyed it. And by the way, one thing that I will say is I'm currently still working on the compiler. It works, but I want to clean some stuff up with it, tidy little things up, do a little more error checking and error handling with it, so it doesn't, flat out crash in some cases. And eventually what I'm planning on doing is it's going to be up on my GitHub, so eventually whenever I get to finishing it, I'm thinking there's probably going to be a blog post about it too, which if you don't follow Dark Assassins Inc. on our 2 social media sites, which I don't blame you if you don't. We don't really post anything on there. The only thing we post is like when the podcast episodes come out. But if you want to see the blog post before I'm able to announce it on a podcast episode, we will be sure to post it on those the links to the social medias in the show notes below if you have any interest in following the nothingness that we post. But anyway, going back to that trivia question, I did not forget about it. What is, just to refresh your memory, what is the maximum data transfer speed of dial-up internet? Now, if you said 1 megabit per second, you're wrong, because that is not right. You got to go way lower than that. The actual answer is 56 kilobits per second. So if you said 56 kilobits per second, congratulations. Which, we like context on this podcast, right? I've mentioned that before. So if you recall back to when we talked about network speeds, I brought up a situation or a scenario that me and my friends back in college would like to go through on how fast networking speed was, and that was how fast can you download GTA 5. So at the whopping 56 kilobits per second, you would be able to download GTA 5, which is around 95 gigs or so, in 157 days. But seeing that someone's probably going to want to use the phone at some point, you're looking at much longer than that, and that's also assuming that you'd be able to gracefully pause the download before the person picked up the phone and didn't completely corrupt your download and you'd have to restart from the beginning. So yeah, not really ideal to download GTA 5 on dial-up internet. I mean, if you want to be an absolute madman and go for it, by all means, I'd love to hear the story, but honestly, I cannot personally recommend, because, like I said, if you're, downloading GTA 5 on your dial-up speeds, and then in the middle of the night there's an emergency and the phone rings at your house, someone picks up, but you couldn't pause the download, and you were on day 156, that's gonna be rough, because you were right there, you almost were done, and then it all got corrupted, you have to start over again. So, yeah, that's dial-up internet for you. A whopping 56 kilobits per second was the theoretical maximum. Now, were you actually getting 56 kilobits per second all the time? Probably not. But that was the maximum speed that you could have achieved. So, if you enjoyed this episode, I ask that you leave it a rating and review and subscribe to the Dark Assassins podcast if you haven't done so already. Also, be sure to share it with a friend or family member who would be maybe interested in learning about how numbers on a computer work, how signed unsigned integers work, hearing about this new fancy dynamic cluster compiler that I made, or hearing about ChatGPT in schools, or any of the good stuff that we talked about on this episode. Maybe it was the cybersecurity tip that you want to share with a friend or family member. I don't know, but share with them. And if you have any questions about this episode, or you have any recommendations for topics to cover in a future episode, you can send me an email at contact@darkassassinsInc.com, or you can click the link in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.